Moving on to free response number 5. We'll not need a calculator here either. Lewis, you need to know Lewis structures in the back of your head. So immediately, they like me to draw the Lewis structures for each of these. I'll let you guys go ahead and do that. But this one is going to look like this. You might want to show your lone pairs always. I'm going to do it for 1, but it'll be a good idea to show your lone pairs always for this test. Notice there are lone pairs on the central atom here, which does bend this bond down. Okay, CH4. And draw the wedge there just to note the tetrahedral structure of that. And now O and S have similar properties because on the periodic table they're in the same column. So they have the same number of valence electrons, thus similar properties. So their Lewis structure is going to look the same. Predict the shape and the hybridization. So SF4, 4 things are attached. We have 1 lone pair. We're going to call that seesaw. And 4 things and 1 lone pair is 5 things. So that's sp3d. CH4 is tetrahedral. And that's sp3. And again, OH4, similar properties. It's going to have the same shape. Seesaw, sp3d. Which substance above has the highest boiling point? Okay, when you think back to our boiling point chart, ionic compounds are the stickiest. I want you guys to remember that. If they ever gave you an ionic compound, you know that's got the highest boiling point. One way of thinking about it is all ionic compounds are solids at room temperature. Think about like water. We think of water having a high boiling point because of its hydrogen bonding, but it's still a liquid at room temperature. So salt, for instance, NaCl, table salt, will have a higher boiling point than water. Even though water has the hydrogen bonding, salt is ionic. We have the 2 polars. We have the polar with H bonds. Remember, an H bond is every time you have H connected to N, O, or F. Polar without H bonds and non-polar. So let's go up here and let's identify these. This one here is non-polar. This is polar. And this is polar. This is non-polar because it's symmetrical. We also do not see any lone pairs in the central atom. These both have lone pairs in the central atom, and OH4 has O connected to H. Okay, so that does hydrogen bond. It's going to be right there on the chart. So OH4, it's polar with H hydrogen bonds. Okay. D, they're listing some bond energies here for the combustion of methane. So let's go through and answer these questions. 1, right imbalance of combustion of methane. CH4 plus 2 O2s goes to CO2 plus H2O. We're going to have to put a 2 there. 2, give the balance of reaction and the bond energies in the table. Write an algebraic expression that could be used to calculate delta H. Well, I do see the word bond, so delta H is going to be equal to broken minus formed. Okay, so let's expand this. My bonds that are broken, okay, are these. All these bonds have to be broken, and 2 of these. And my bonds that are formed have to be those, and 2 of those. So I need to get values for that. So my value for this on the chart, the CH bond, is A. So I'm going to get 4 times A. My value for the double O bond is B. So I'm going to get 2 times B minus 2 of those C double bond O's, 2C, plus 2 of the OH's due to the coefficient, 2D. And there's the algebraic expression. You don't need a calculator on this section, so that's why it happened. What do we predict the value of delta H to be? It's combustion reaction. Also see the word burning. Always produces heat, releases heat, so delta H is less than 0. exothermic. Based on your answer, draw an energy diagram for this combustion and sketch in the effect of the catalyst. Yeah, so energy, we can put time here. It's exothermic, so that's delta H. This is the EA, and there's the effect of the catalyst. Decreases the Hill. Now, be aware, a spark plug, increasing temperature, increasing concentration, increasing surface area. All of these things push you up to EA Hill faster, push you up faster, push you up faster. A catalyst decreases the size of the hill, okay, by providing a different route. Say we had a reaction, the catalyst is always regenerated as well. It's not an intermediate, it is regenerated. So that's the way this looks. You could also add in the reactants, the actual chemicals on each side if you'd like to hit some extra time. Alright, 6 asked us to answer these following questions about electrochemistry. So just like on free response number 1, you're going to immediately do an ICE. If you see an electrochemistry problem, you're immediately going to write anox, red cat, and you're going to label the anode and the cathode. Well, we have Zn and we have Ni. If you look on the reduction potential chart, Ni is higher than Zn. So that's the cathode and that's the anode. So cathode, anode. Now electrons always flow from the anode to the cathode. So electrons are going to be going in this direction. Makes sense because if the anode is oxidized, it has to be losing electrons. And if the cathode is reduced, it has to be gaining electrons. Leo goes Gur. Losing electrons is oxidation. Gaining electrons is reduction. You could also think of it as oil rig. Oxidation is losing electrons. Reduction is gaining electrons. Alright, so let's go through this. Label the anode, the cathode, and the direction of electron flow. We did that. Notice that happened before we even started. Write the half reaction that occurs at the anode. So at the anode you flip. So the anode contains Zn. So Zn is going to be flipped from what we see on the chart. We're going to show the oxidation half reaction. Cathode, we're going to keep the same. Nickel 2 plus 2 electrons goes to nickel 0. Write the overall reaction. Alright, so everything that's on the left side of the reaction, Zn0 plus Ni2 plus, and everything that's on the right side of the reaction, Ni0 plus Zn2 plus. And calculate E. So E equals E ox, negative Ex plus E reduced. So negative, the oxidation potential here for, you should flip it, right? So negative 0.76 plus negative 0.25 equals 0.51 volts. Predict whether this reaction is spontaneous. Well, delta G equals negative NFE. If E is greater than 0, delta G is less than 0, therefore spontaneous. What would happen if E cell, what would happen over time if the battery was allowed to run? Okay, so over time, E cell would go to 0 as you run out of electrons, and delta G would increase to 0 as well. I'll do the last problem real quick here. I have like 30 seconds. Actually, well, 3 minutes. I want to take my time on this last problem, so I'm going to set up one more vodcast for that. So again, if the battery is allowed to run, it's going to run out of electrons. If it didn't change, the energy crisis is completely solved. We know that 9-volt batteries do not last forever. We know that AA batteries do not last forever. Their E cell goes down, therefore their spontaneity goes down, thus delta G goes up. See you guys in a sec.